So as everybody can probably tell, my name is not Sean Darcy. Sean was unable to make it due to a medical issue. Unfortunately, Sean didn't send me a slide, so I put these together last night. We'll see how it goes. And again, so I was actually pretty inspired by Travis's talk. So I don't have a cool picture of a car. What I do have is a cool picture of the first picture of the black hole that anybody's ever taken. So Einstein's general theory of relativity, it predicts that a sufficiently dense mass will cause black holes. And we've been able to notice this just because stars don't rotate the way they're supposed to. Something must be pulling on them, therefore, hey, black holes must exist. And in April of this year, people were able actually to take pictures of the radiation that's caused at the event horizon. And that's what this picture is right here. So this is in the middle of the Messier 87 galaxy, which actually just won, it was announced last week, it just won the Breakthrough Prize in Fundamental Physics, which is pretty awesome. And this radiation, it hits the Earth at 230 gigahertz. So the wavelength of the radiation is 1.3 millimeters. And if you were to point a telescope from the Earth to where this galaxy exists, you would need a resolution of 1/millionth of an arc second to actually see it. And for those people who are involved in astronomy, you know that it's like, oh, that's pretty small. But what that means is if you were to make one satellite dish to try and measure that, you'd need a satellite dish of 8,000 kilometers long in diameter. Since that's not practical, what they end up doing is they have multiple satellite dishes actually across the planet, which has a much different challenge. So now all of these satellite dishes need to be actually synchronized. Their sample rates need to be synchronized. Their sample rates need to be synchronized to the point where they would slip 1 second over 1 million years. The sample rate, like Michael was talking about earlier, they only take 2 bits. That's what they store on their hard drive. But their bandwidth is 16 gigahertz. So they take that 230 gigahertz, downsample it to 16, or down-convert it to 16, and then sample it at 16, and store 2 bits on their hard drives. And these hard drives are neon-filled hard drives because they actually create 350 terabytes a day when they were storing it. So they basically created 5 petabytes of information. And that would be 5 million gigabytes. So when they were done their experiment, it was faster for the guys in the Hawaiian observatory to take the hard drives, jam them in a suitcase, put them on an airplane, fly to Boston to MIT's Haystack Laboratory, and unpack them there and connect them back up. And even based on that, they got 14 gigabytes per second, which is a pretty reasonable link for anybody. So that they couldn't transfer any of the information over the internet. They had to transfer everything by suitcase. And when you think of these things, like they have to handle scattering, water vapor in the atmosphere, frequency stability. They have to actually correct for movement into the tectonic plates. They have to correct for changes in the ocean's tide. All these kinds of things are huge, huge computational things that people are trying to figure out when they're putting this information back together. So this was the accumulation of 200 different researchers in many, many different application areas. And it was a big breakthrough for lots and lots of people. And the key point about this isn't that it's just cool, but also it's very multidisciplinary. It's not just signal processing, it's not just radio astronomy, it's not just compute pieces, it's not just Python, because a lot of the algorithms they actually designed to make the picture were actually designed in Python, where they would load up their 5 petabytes of information into Python. And when it comes to analog devices, what we do is we do some of those similar kinds of things. We take the physical world, we sense, measure, interpret, connect to that digital world, and also power it. And on the RF side, it's the same kind of thing. We're connecting that electromagnetic spectrum up to that digital world. And just kind of an example of how this has changed over time and how we're doing more than just RF. Because even in the RF domain, it's more than just being a good RF engineer. You have to understand digital comms, you have to understand digital algorithms, you have to understand all these digital pieces. So we'll just look at a communications example for now. So if we look at an LTE base station from 2012, the board was pretty giant. It had 2 receivers, 2 transmitters, and 2 observer paths on it. And if you look at the block diagram on the right there, there's mixers implemented in bi-CMOS, ADCs, and the orange kind of pieces that are implemented in CMOS, and then the purpley pieces are all discrete filters. So these were hugely large on PCBs. And then, from CMOS integration, we could basically take that down to 1 chip, even in 2013. But that was more for single carrier kinds of applications. So we'd have a single carrier, and that blue area on the side of that die was basically digital assist. It was digital algorithms fixing imperfections in the CMOS technology to make it perform as good as a discrete implementation. And for single carrier, it was pretty good. And lots of people deployed this kind of thing. But it had a pretty modest dynamic range for LTE. But if you are a base station person, especially in 2015, 2016, you want to make a single base station and deploy it worldwide, which means that you still have to support GSM on your base station. And GSM has much different constraints in your system, and the level of performance that's needed is much, much higher. So one of the things we learned when we went from GSM to LTE was GSM has a lot of crazy constraints on it, and LTE is much easier. But to support all these legacy phones, to support all these emerging countries, everybody wants to make base stations that support both. So the die size gets bigger, it's still 65 nanometer. And the bigger in the analog section is mainly just getting that extra 50 dB of SNR improvement. But you can also see the digital section more than doubles or triples. And that's more digital assist to correct for all these algorithms. So it's still just 2 receive, 2 transmit, but it's a much higher performance. And then we can go to things like massive MIMO. So now we've actually gone to 28 nanometer. We have 4 transmit, 4 receives with digital pre-distortion. And again, now the digital piece is almost a quarter of the die. And as we go to multiband, it's even much bigger. So the digital assist pieces are almost half of the die compared to the analog sections. And that's super digital, complicated filtering, IQ correction, compensation, because the level of performance we need to do on these next generation devices is we actually have to do calibration and correction over voltage, calibration and correction over temperature, calibration and correction over frequency, calibration and correction over all these different things where the chip can vary because CMOS is such a terrible, lousy process to do RF on. But CMOS is great in terms of a price point, great in terms of integration, and great in terms of adding digital. So it's much easier to do these kinds of things, but it requires different skill sets. And so it's that merging of everybody's ideas together. So we can kind of see this evolution of how that digital has moved and grown in the system. And as that digital is moving and grown in the system, one of the things that we've looked at and said, okay, well, now that we're adding all this digital pieces into the RF transceivers, what new capabilities are people actually asking for that we could add? And the obvious one, which I think we've talked about before, was digital pre-distortion. So if we look at a chip where a digital pre-distortion is done off the chip in an FPGA, typically the receive section or the observe section has to be running at 5 times the bandwidth, and that requires a huge amount of power just to transfer the data back and forth between an FPGA and the transceiver chip. And so you can think of like now, instead of running at 100 megahertz of data running across the device, now you have to run at 500. And every clock edge is power. So by taking that DPD function and putting it into the transceiver, by putting the actuator in the transceiver, we can actually run the interface at 1/5 of the rate. We go back to 100 megahertz, and we save giant amounts of energy. So we can shrink that FPGA down, save some cost, as well as what our customers tell us, is in like 64 transmit, 64 receive systems, and these massive MIMO systems, they save 100 watts of FPGA, like a system power, because they're not doing these things in the FPGA anymore. They're doing them in a fixed ASIC. And so when we kind of look at this, kind of looking back, what we've kind of called this, and what other people have called it, is this recombinant innovation. And this is actually a book which is pretty good, by Andrew Hartigan. He's UC Davis, and this is like circa 2003, but it's like, existing technologies are usually combinations of objects, which in this cases are like hardware, software, the ideas, like how those things interact with each other, and the people. And the people are the most important thing. And it's the people who know the ideas and objects and how they can work together to actually get that benefit. And one of the things he says in this book is innovators are no smarter or no more courageous than the rest of us. They are simply better connected. And I think, I'm hoping that's why everybody comes to conferences like this, so they can remain connected. Like listening to the presenters and listening to me drone on, I'm sure is interesting, but the biggest impact you probably have is talking outside, talking to the vendors, talking to everybody else, trying to learn what other people are doing and how you can leverage those good ideas in your projects. So, when I first started out in my career, I always wanted to be the smartest guy in the room. Now, as like an engineering director, you want to be the dumbest guy in the room. You want to hire people smarter than you. And you want to make sure that these people get ideas together and are driving things all in a common manner. And that kind of goes into, Analog Devices always hiring. We, in the US, if you would just look under engineering jobs, we have 65 engineering jobs open. And these are from RF design to digital design to systems engineering to algorithm development to everything. Like, because of some of the things that we're doing in the healthcare area, we actually have physicians on staff, which is pretty crazy. Can you imagine going to medical school and then getting a job at a semiconductor company? That'd be pretty crazy. That's no worse than getting your PhD, I guess. So, all these technologies are really driving tomorrow's innovations, whether it's from autonomous transportation to machines to 5G to digital health, Industry 4.0 or immersive consumer. And when it comes to ADI, we've been around for a long time. We have 15,000 employees, but we have 125,000 customers. And so that's a lot of people doing lots of very diverse things. And people trying to leverage what we know in their end designs, which is great. That's what we want to be able to do. So that's why when we come to conferences like the GNU Radio Conference, we try and do a lot of things. We've done a lot of presentations. Apologize for being this my third talk. But we also have like a lot of demos, which I hope everybody comes over and sees, from 4RX, 4TX phase coherent system on a module, to the Pluto Phosphor, where we actually do FFTs and log inside the FPGA, the Pluto itself, to the ALM2000 radio, and then fast frequency hopping. But Analog Devices has about 45,000 different products, everywhere from amplifiers to switches, multiplexers, power, data op. There's lots of devices that we make which go in everybody's application. And then we kind of look at it from a market perspective. It's aerospace defense, it's healthcare, it's communications, it's instrumentation, it's autonomous, it's energy, it's power. And there's a lot of people that come up to me and say, okay, well, what group am I in? And my group and the other people that are here from ADI, we don't belong in any of these things. So what we're actually in is called our Systems Development Group. And we're so special in the company, we don't even get the same logo as everybody else. But what we try and do is try and make it easier for people to design in the complex parts that ADI makes. So for example, this device, the ADR V9000, was released 2018. You read through some specs, it's kind of neat. And the big piece that everybody looks at is like, oh, phase synchronization on the chip. Synchronized LOs, synchronized baseband. That is a big deal. But when the business unit who made it, they took traditional semiconductor kind of thought processes. You take one chip, put it down on an eval board. It's like, okay, well, show me it actually synchronized. And it's a lot of hand waving and a lot of data sheet pointing, and it's a lot of like, go read the manual yourself. And it's hard for people. So what we did in our group is we actually designed this system-on module with 2 radio chips on it and a zinc. And people actually take this and are using this for their designs now. Here we go. So it actually has 2 radio chips, a zinc, 4 gig of memory for the ARMs that are in there, and 4 gig of memory for the programmable logic standpoint. And people are actually deploying this in radar systems today, and to show that it is synchronized, it can be synchronized. And then when we get this to some of our customers, they go, hey, this is neat, but how do we synchronize multiple of these together? Because if you are an aerospace defense company making a 1,000-element radar array, synchronizing 2 is like, okay, you show me it works, but how does it scale? And so one of the demos that we have over there isn't in this quite backplane, but it actually shows 2 of these SOMs synchronized together to get an 8x8. And depending upon what you're looking for, we also work with a lot of third parties like our customers like Epic, which have taken the Pluto design and actually shrunk it down into a tiny form factor, industrial, ruggedized, runs over temperature, these kinds of things. So if you start out on here and get to a point, it's like, hey, this is pretty neat, but I need something that's ruggedized, I need something that's industry worthy of being deployed out in the rain up on a mast, then you can actually get that from other people. So some of the other, the group that I'm in, we don't just work on radios or comms. We also do a lot of other things like 3D time of flight. So this is a platform that is a 3D imaging camera that will give you images like this. They will connect up to either a Raspberry Pi or a 96 board. Here's a LiDAR platform. So this is a 1D LiDAR where it'll shoot out some lasers and then get the reflections back. Goes into a very, very high-speed converter in the FPGA and can see it. So there's all kinds of sensing technologies that we're working on, from 3D time of flight to LiDAR to radar. We also do a lot of other things like Arduino Shields. So these are just Arduino Shields with RMS power detectors on them that some people are connecting to Arduino and using as, like Peter was talking about, low-cost instrumentation replacement. And we do a lot, again, with universities, working with both circuits, communications, power electronics, and these fast prototyping. So, we do actually have some giveaways on the demo. If you come over and give me a card, if you're a faculty or a student, we can probably set you up. And definitely, I think the workshops tomorrow are actually full already, but there may be some devices left over on Thursday. Just come by. So with that, I just want to say, thanks very much, and maybe we made up some of our time. Yeah.